In this video, we're going to be taking a look at 3.4, which talks about this thing called the chain rule. It's very important that you understand all of the other rules that we've talked about so far, especially the product and quotient, as we work on the chain rule. So let's go ahead and begin. First of all, let's look at the definition of the chain rule and how to tell exactly when to use it. So number one, you want to identify it as composites. Right, and remember, composite would look something like f of g of x, where you have one function nestled inside of another, or f of g, kind of looks like fog, but that's what that stands for, f of g. So number one, identify it as a composite function. Next thing is you want to go ahead and identify your u function, which is your inside, and your f of u function, which is your outside function, and we'll do examples of that as well. So that's step number two. And step number three, you are going to want to find the derivatives of those inside and outside function. Okay, and then once you've done all of that, the fourth step that you're going to want to do is to go ahead and find the derivative of the function by taking the derivative of the outside. So that's this right here, but the derivative of the outside would look like this right here, times the derivative of the inside, which would look like that. Okay, so the derivative of the outside right here, you want to leave the inside alone. So leave this alone. This does not change. So the inside function does not change when you're finding the derivative of the outside. So on that first step, that inside doesn't change, and then multiply by the derivative of the inside right here. I've heard it once said like this, right? So imagine you have a mom that is expecting a child, so she's pregnant with a child, and the child is the inside function. So take the derivative of the mom, leave the baby alone, then multiply that by the derivative of the baby. So it's the derivative of the outside, leave the inside alone, times the derivative of the inside. Go ahead and write that down in whatever way that would help you remember that, and then let's move on. So with these examples, what we're going to do is we're going to go ahead and identify the inside, identify the outside, and then find those derivatives, and then find the derivative of our function overall. All right, so for the first one, the inside is going to be, if you look at this, is not one that's necessarily a composite function. So we could just do on this one, it would be the quotient rule. So it would be the low, so x plus 1, times the derivative of the high, minus high times the derivative of low over low. So x plus 1 quantity squared. And then that would just simplify to negative 1 over x plus 1 quantity squared. And so right off the bat, I on step number one, identify as a composite. That's not necessarily a composite. We can just apply the quotient rule. Okay. Number two, the second one down here is not necessarily true. So we're going to go ahead and identify our inside function and then our outside function. And then with both of those, we're going to find the derivative of the inside and the derivative of the outside. So our inside for this next one is going to be what's inside that square root. So it's this function right here. That would be 3x squared minus x plus 1. And the derivative of that's going to be 6x minus 1. And the outside is going to be the square root itself. So the outside function looks like this. And remember that inside stays the same. It does not change. That baby doesn't change. So we're going to go ahead and find the outside, and I'm going to write it instead of a square root, I'm going to write it as, so we're going to put u in there. I'm going to write it as to the 1/2 power. Remember, u doesn't change when we find the derivative. So it's just going to be 1/2 u to the negative 1/2 is the derivative. Now what I'm going to do is go ahead and to find the derivative, I'm going to go ahead and multiply this and this together. More accurately, that and that together. But when I do that, I'm going to take this u and substitute it back in there for u right there. And so our derivative, so y prime, is going to be 6x minus 1 times 1/2. Instead of u, it's going to be the 3x squared minus x plus 1 quantity. No, that's not quantity squared, but that's to the negative 1/2. And if you rewrite that right at this point, you can stop, or let's go ahead and keep going. There's not much further that we can go, but we can distribute this 1/2 x in. So you would get then 3x minus 1/2 all over the square root of 3x squared minus, not plus, minus x plus 1. And that would be as far as you can go. And I flipped it to the bottom because of that negative exponent right there. All of this went to the bottom. Go ahead and try this one on your own right here. Pause the video, try it on your own, and then come back to see how you did. Okay, let's kind of walk through the steps here. First of all, we find our inside and our outside functions. Again, our inside is just identified as u, which is x squared plus 1, and then our outside is just the inside to the third power, so u to the third. And then when we find those derivatives, and we're going to end up just multiplying those derivatives together, so 2x times 3u squared, looks like this. And this is our answer right there. So if you're asked just to find the derivative, you could stop there, but I highly encourage you to go further to simplify it pretty much as far as you can go. And I would probably even stop here. You could go ahead and square that out like this. You could square it out and then multiply that 6x in. But I think right here, this is in factored form, so it technically is simplified, and this is just expanded form. So either one of those would be ideal. Now go ahead and try s of x, try to figure out what your inside, your outside functions are, and then go ahead and differentiate this one. There are two different ways to do this, because if you do inside outside, you notice there are two nestled function inside one other function. So there are 3 layers in s of x, because here you have your inside, then you would have your inside of the square root, and then the cube root, and then your cube root would be your outside. If you want to try that, you can. You're going to end up just multiplying all of those derivatives together. But there is another way to think about this before you go ahead and start finding the inside and the outside and find the derivatives. Let's see if you can't do it one or the other ways. Probably the one way that would be the easiest, instead of doing 3 layers of composite functions, which is totally possible, just a lot more algebra involved, is if we simplify or rewrite it a little bit right at the beginning and go ahead and multiply the squared to the cubed root, which is what I did right here, and I get x squared minus 1 to the 2/3. Now from here, we can identify our inside and our outside functions much more easily and find the derivatives of those as well. So from here, if you haven't gotten this far, pause the video before you move on. So if we look at what we have our inside and our outside functions, derivative of our inside, derivative of our outside. So times derivative of the inside to the derivative of the outside, leaving the original inside, that u function right here, we leave that alone. It does not change at this step right here when we find the derivative of the outside. And then we just multiply them and simplify them. And I think right here is about as far as we're going to be able to go on this one. So hopefully this is making a little more sense. So let's take a look at g of t. Now with everything that we know how to do, it kind of opens up what we're able to do, because g of t, there's a couple different ways you could go ahead and do this. Like on the bottom, if you wouldn't just multiply out the 2t minus 3 quantity squared, multiply that out and then use, the other methods that we've learned, or you can use the quotient rule, or you can just straight up use the rule that we've been using by taking the 2t minus 3 to the second power into the numerator and making that a -2 exponent. It's entirely up to you. Go ahead and try it one of those three ways and kind of see if we're able to land on the same thing. Okay, let's see how we did on this one. So what I did is I just kept it as it is and ended up doing the quotient rule. But to find the derivative of this bottom one, I went ahead and did that because I found my inside and my outside. Derivative of the inside, derivative of the outside. So when you do the low d high, that's going to end up being 0 because the derivative of -7, the slope of -7 is always 0. Minus, then it's going to be the high times the derivative of the low. And when you simplify all of that, you get 28 times the quantity of 2t minus 3. And do not distribute that 28 because the 2t minus 3 will cancel with one of those in the denominator. And this is your final answer. For this one, there's going to be other rules that you're going to have to apply for this one. In this case, you're going to have to be using the chain rule along with what we just learned about the chain rule and the product rule. There we go. On this one, so go ahead and try this one. Pause the video, try this one, and come back and see how you did. Okay, so let's see how we did here. Now we're going to take what we have and maybe go a little bit further, but first, using the product rule, just took the derivative of the first times the second, so the derivative of x squared times this square root of 1 minus x squared function. Now here's where it comes tricky because it's the first, which is x squared, times the derivative of the second. So here, let's follow my arrow. I went ahead and identified the inside, the outside, did find the derivative of the inside, derivative of the outside, and then multiplied them together, simplified it down to something like this. And then I went ahead and that's what I plugged in right there. Okay, so then that is the derivative of the right or the second function in this product rule. Now, this is the derivative, but I'd highly encourage you, because looking at this will simplify down a little bit. We will be able to combine them because if we take and multiply each side by the square root of 1 minus x squared, then we'd have common denominators. So let's go ahead and do that, or multiply the left side, by square root of 1 minus x squared over the square root of 1 minus x squared. However you want to do that. Let's see if you can't simplify it down. There are multiple different ways to where you could actually stop in this case, but let's look at this. What I did is I went ahead and multiplied the left function, the 2x times quantity of 1 minus x squared to the 1/2 by square root of 1 minus x squared over the square root of 1 minus x squared, so it would have a common denominator. So now they have a common denominator. Then I went ahead and I multiplied this 2x in. And when I did that, I got 2x minus 2x to the third. And then on the right side, I went ahead and multiplied these together, and that's where the negative x to the third comes from. Then I just combine all of the like terms, and this is as far as I got. Now, this is the expanded form. You could factor out an x out of the numerator. You could definitely do that, but I'm just going to go ahead and leave it like this as our final answer. You should have come up with something very, very similar to this. Now go ahead and try this one on your own. This is using, looks like, the quotient rule along with the chain rule, and see how you did. Pause it and see how you do. So looking at this one, it's quite a doozy. There's quite a few steps. Now, there's other ways that you could probably do this, like right off the bat. If you just simplified this or rewrote this as 3x plus 1 quantity squared over x squared plus 3 quantity squared, and then actually multiplied those out, it'd be maybe a lot easier. I'm not really sure, because then you'd have pretty big polynomial functions. But let's take a look at what we have. What I did is I went ahead and kept it as it is. My inside function was identified as 3x minus 1. My outside, 3x minus 1 over x squared plus 3. My outside function was u squared. And then when I find the derivative of the inside, that's the tricky part. That's where you have to do the quotient rule. So low d high minus high d low all over low low. And then I simplified it down as far as I could go, which was right to there, right to that point. Then you find the derivative of the outside, which is just 2u, and you multiply those two things together. When you multiply those two things together, I went ahead and took this 2 and multiplied it into all of these terms right here, which is where these terms come from. And then my u function was just that right there, which is this. You could probably keep it there, but then I noticed, hey, this will go ahead and combine with the denominator there. Instead of to the second power, it would just make it to the third power. And then I just kept the top as it is. I think this is about as far enough because it's pretty much as simplified as you can go. Otherwise, you'd expand it even further. You could even leave that 2 outside. I know I multiplied this 2 into here, but you can even leave that 2 out here. So I'd say if you were able to get to this point or something similar to this, that would be amazing. But right here, if you were able to get to this point, that's the derivative of the function, and that would be just fine too. But I always strongly encourage you to try to simplify it if you can. So really, the rest of this video is just a bunch of examples. So here's 2 more. Go ahead and try these 2 with the cosine of x minus 1 and e to the 3x, thinking about, well, I know these are composites because I have this function inside, and then I also have this function in the exponent of my e. What do I do with that? Go ahead and try these on your own. Identify your inside-outside functions and go from there. So if we look at the derivative of the cosine of x minus 1, your inside is x minus 1, your outside is cosine of u. Derivative of the inside, derivative of the outside, we go ahead and multiply those, and that simplifies down to negative sine times the quantity of x minus 1. And let's go ahead and take a look at e to the 3x. We'll go ahead and for e to the 3x, the inside function is 3x, the outside function is e to the u. Derivative of the inside, derivative of the outside, we go ahead and multiply those, and we get y prime, the derivative is equal to 3 times e to the 3x. So fairly simple, as long as you can identify the outside and inside functions there. Go ahead and try these next 2 on your own. Y equals cosine 3x squared and y equals cosine squared. So in this one, it's the cosine function being squared, not your x, not the inside function. It is the outside function that's being squared. So if you need to rewrite that so that makes a little more sense to you, go ahead and do that. But pause the video, try these on your own, and then come back and see how you did. Looking at the first one, we identify our outside and inside. So inside, outside. Derivative of the inside, derivative of the outside, multiply those together and simplify. That's as far as you can go. Looking at the next one, if you were not able to try this one, make sure you go ahead and try it and then come back. But another way to write this is cosine of x all squared. So cosine of x, all that quantity squared. So now you might be able to identify more easily what your inside and your outside functions are. So pause the video and try this on your own. And again, we identify our inside, outside, derivative outside, and then multiply those together and simplify. And this is about as far as you'd be able to go on this one. So here's an example of when you would have to apply the chain rule more than one time because you have 3 functions, kind of 2 functions nestled inside another primary outside function. So you have to identify all of those. So go ahead and try this one on your own and see how you do. You identify all of them, all of the functions, the outside, the inside of the outside, and the inside of the inside outside. Yeah, you know what I mean, right? So you have the 3 functions, find the derivatives and multiply them together and simplify. All right, so if you pull this apart, you have 3 functions. You have your inner inside, which is the 4x right there. Then you have your outer inside, which is the sine of 4x. and I just use u because I substituted 4x in for u. And then you have your very outside, which includes that power to the third. And I said that that's your g function with your f of u function, which is your sine of u function inside. And so it's just f of u to the third power. And I went ahead and found the derivative of all of those and went ahead and multiplied all of those together, plugging the f of u, the u back into what was substituted in for them originally. Then this is what I have. And then from here, you might be able to simplify it a little bit further. And really the only thing that you could do is you could go ahead and multiply this 3 and that 4 together. And that's as far as you can go, making it 12 cosine of 4x times sine squared of 4x. Don't forget about this squared outside of this sine of 4x there. And this is as far as you can go for this one. Let's go ahead and take a look at how this applies to natural log functions. Go ahead and try this one, the natural log of 2x, identifying your inside and outside function and finding the derivative of those. So if we identify our inside-outside functions, the inside would be 2x, the outside would be natural log of u. We find the derivatives of those, and we go ahead and multiply them together. So you get 2 times 1 over 2x. And when you do that, you get just 1 over x for the natural log of 2x. All right, I just realized that this was still on as I was going to take care of something. Sorry about that. So now let's take a look at definition of exponential function with base a. And so if you have something that has a base of a, so let's say it's a to the power of x, that is just going to be the natural log of your base, which is the natural log of a, times the function itself. Whoops, not x, a. So the natural log of the base times the function itself. Now let's take a look at this in terms of what we're doing. So what if it's a composite function? So a to the u, where u is a function. Now that's very, very similar. It's still going to be the natural log of your base times the function itself, but then it's going to be times the derivative of that function. So whatever that function is, this right here is just another way to say u prime. Okay, so all of this right here means u prime. So if it's a composite function, you just multiply by the derivative of that exponent, that function in the exponent to begin with. Okay, now let's take a look at logarithmic functions with different bases. And so here we have a log function base a of x, and we're going to also look at how is that similar or different from log base a of u. Okay, and in fact they're very similar, very much like the one before, but the derivative of log base a of x is just going to be 1 over the natural log of a times your x. So again, that's just either a constant or it's a function that has a derivative of 1, but if it's anything other than that, we're going to be using this one down here where u is a function. It's going to be 1 over the natural log of a again, and then it's just going to be times u, and then you're going to take that times the derivative of u, and that can be denoted as du over dx. So you can see they're very similar, very much the same, and most times that function, which is in the x or the u position, is going to be a function and not necessarily just a constant. Okay, so for these, most time you're going to be using those definitions. So let's go ahead and apply some of those rules to find some of these answers here. Pause the video, try some of these on your own and see how you do, and then come back. Okay, if we take a look at these, for the first one, it's going to be pretty straightforward. It's just the natural log of your base times your function, and in that case, your exponent is just x, so it's pretty simple. On the next one, it's the natural log of your base times your function times the derivative of your exponent. In this case, it's just 3. And then you can simplify that, but you can't really do much with it. If you looked at this a little bit different, because this will actually simplify x to the 8th, and if we do this, it's a natural log of 8 times the function 8 to the x. And these are, if you look at them, the same thing, because this is 8 to the x, and then natural log of 8, you can rewrite that as the natural log of 2 to the 3rd. That's the 3, and then that can come down just like we did right there. Okay, so you can do it multiple ways and get the same thing. And then the last one here, it would be the 1 over the natural log of your base times what's your inside function times the derivative of your inside, which is cosine, and that's where this negative sign came from. And what I did is I just realized that, hey, I had sine over cosine, which is tangent, and so I just simplified that as tangent, so you're left with negative 1 over natural log of 10 times tangent. Or you can rewrite that as negative tangent over natural log of 10 as well. All right, that was a lot to know, a lot to do, and this is probably as difficult of differentiation as it will get when we're doing the chain rule along with the product rule, along with the quotient rule, along with everything else. There's a lot to remember, so make sure you have those definitions and formulas. I have that sheet on the front that would be very useful, very helpful for you. But this is all that I have for 3.4, which is the chain rule.